Hello, Math 2. I am Mrs. Bricky, and this video is for Unit 2, Lesson 3. We're going to be talking about applications of some of the equation solving skills that we've been working on this unit. So our first few examples, we're going to have some shape-based situations, and then we'll have some examples where we're given an equation for the relationship, and we use that relationship to solve a problem. So as we're solving these problems today, for some of them, it will be appropriate for us to draw a diagram. It's always a good idea to help you think through a problem if you have a diagram with some labels on it. We'll be thinking about different relationships, like an area relationship or a perimeter relationship, and also reviewing the Pythagorean theorem today, which is a relationship between the side lengths of a right triangle, and solving for what's requested. As we get our solutions to these problems, we want to be asking ourselves, does it make sense in the context? And we also want to be paying attention to how our answer should be reported. For some answers, we are going to give a rounded decimal form. On other problems, we are going to keep our answer exact. So it just kind of depends on the problem itself. So our first example, Mike and Lachelle want to make a square patio. They have enough concrete for an area of 200 square feet. To the nearest tenth of a foot, how long can a side of their square patio be? So we have our shape in this problem is a square. And one thing we know about squares is that all of the sides of the square are the same. So we'll call the side length of this square x because we don't know how long it is. In fact, that is what we're trying to figure out, is how long can that side of the square be? Well, if all the sides are the same, then this side is also that same length x. We know that the area of this patio is 200 square feet. They have enough concrete to make it 200 square feet. So 200 square feet is an area. So the area equation for a square or rectangle is length times width. But if the length and the width are the same as they are on this square, you can write that as the side squared, because x squared is just shorthand for x times x. So we know that the area of this square, which is x squared, must be equal to 200. And so we could solve that by applying a square root to both sides of the equation. Now, when we've been applying square roots in equations in previous problems, in previous days, we've been applying a plus or minus symbol here with our square root, but we're looking for the side length of a square. So it doesn't make sense that we would have a negative answer to this problem because of the context. So when I type into my calculator the square root of 200, it tells me that that is equivalent to 10 root 2. But it asks us to round our answer to the nearest tenth, so we do want a decimal answer here. So if we have our calculator convert that into a decimal answer, it is 14.1 feet. I rounded that to the nearest tenth. On your calculator screen, you would see 14.142135, ... and we're rounding to the nearest tenth, which is that first decimal position. Okay, so this is our answer to this problem, 14.1 feet. Let's try another problem. For example 2, we have a diagram of a circle here, and it says that the area of the circle is 20. The formula for the area of a circle is area is equal to pi times the radius squared. And our goal is to find the radius of this circle whose area is 20 square feet. So that 20, that's the area. That's how much space the circle takes up. So in our formula, that's the A. So we're going to put 20 in place of A, and our goal is to solve for R. Well, in this case, we're going to need to, before we take the square root, we have a power of 2, so we are going to square root, but we have this extra multiplication by pi on this side of the equation with the r squared. So we do want to divide both sides of our equation by pi, and that's going to isolate that r squared for us so that we'll be able to use a square root. So 20 divided by pi in our calculator, that is 6.36619 ... I'm just keeping a few decimals. In the end, I'm going to round to the nearest hundredth, which it doesn't say that on my screen, but it does say that in your printed notes. So we're going to take the square root of both sides of this equation. And again, I'm not using a plus minus symbol here because the radius of the circle is going to be a positive amount. We aren't interested in the negative answer here because of our context. Okay, so when we take the square root of 6.36619, we get 2.52. And so this means that our radius is 2.52 feet. And rounded to the nearest hundredth, that does mean 2 decimal places, if you don't remember that from prior years. Our first example, we rounded to the nearest tenth. This one, we're rounding to the nearest hundredth. Okay, example 3, we're back to having a square. This time, we have a square with an area of 72 square inches. So this area is the amount of space that it takes up. So this is 72 square inches. Our question is, what is the perimeter of the square? So remember that perimeter is all the sides added together. So it's the length of the outside edge of the shape. Okay, so again, it's a square, so whatever length this side is, we know this side is also that same length. So we could write down an area relationship here. X squared is equal to 72. This is just, x squared is just length times width. So if we solve for x, we would take the square root of both sides. We're not going to use a negative here because of our context. And the square root of 72, which you can evaluate in your or simplify in your calculator, is 6 root 2. Now this is just one side of our shape. And our question asks us for the whole perimeter. So you can either think about adding 6 root 2 to itself 4 times, or you can just multiply by 4, since they're all the same length. And 4 multiplied by 6 root 2 gives us a perimeter of 24 root 2. And it did ask us to leave that in simplified radical form. So that is our final answer. Okay, this example 4 will be our last shape-based example. So we have 2 right triangles on the screen here, and it asks us to solve for the unknown side of each of these 2 triangles. And when we get our answer, we're going to try to leave that answer in exact form. We don't want to round. So because these are right triangles, we're able to use the Pythagorean theorem to help us solve. So Pythagorean theorem is only a relationship for right triangles, so we do have to have that marking that tells us that it's a 90-degree angle. And for right triangles, if we take the leg squared and add it to the other leg squared, it's equal to the hypotenuse squared. And remember that the hypotenuse is always the longest side in that right triangle. It's the side that is opposite from the right angle. So we're going to write down an equation for these triangles and then solve for x. I want to emphasize that it is actually very important in this class for us to be writing these equations down. Oftentimes, sophomores who come here have used the Pythagorean theorem before, but the emphasis in your past classes has often been to just type something in your calculator and get a decimal answer. So I do definitely want to emphasize that you should write down your equation. Now, once you have your equation written down, if you know how to input it into your calculator to solve from that written equation, that's fine, but please write your equation down. The main reason that we have you write the equation down is that a lot of errors occur when people just use their calculator and never write down an equation. And if you don't see the equation written, it's much easier to make a mistake than if you have a written equation. The written equation usually helps you see a correct path. Okay, so in this triangle, our two legs are x and 24. So we have one of the legs squared plus the other leg squared, and that is equal to the hypotenuse, which is 25 squared. Now, it's a pretty good idea if you are prone to making errors to actually calculate these numeric values. So I'm going to go ahead and do that. 24 squared is 576, and 25 squared is 625. So if we solve for x squared, or if we get that x squared isolated so that we can finish solving for x, we're going to subtract 576. That gives us x squared is equal to 49. And now we can apply our square root, and we can get our answer x equals 7. Again, I didn't use a plus minus symbol here because it's not going to be a negative 7 side length. This is x equals 7 for this shape. Okay, this next one is a little bit more challenging, and definitely we would want to write down an equation here. So this is called an isosceles right triangle. It's called isosceles because this leg and this other leg are the same. So our math vocabulary word for a triangle that has two sides that are the same length is isosceles. So we have an isosceles right triangle. So when we use the Pythagorean theorem, or we write down a Pythagorean relationship here, it looks like x squared, so that's one of the legs squared, plus the other leg squared is equal to the hypotenuse squared. Well, the right side of this equation, we really have a 1x squared plus another 1x squared. So that gives us a total of 2x squared. And 8 squared is equal to 64. So I've simplified both sides of my equation. Our next step is that we're going to divide by 2 so that we have the x squared by itself. And then our last step is that we're going to apply the square root to both sides. I'm not using a plus or minus symbol here because I'm looking for a positive side length. When we take the square root of 32, we can simplify that in our calculator, and it is 4 root 2. So on this second triangle, our side lengths are two legs that are the same length. They have a length of 4 root 2. Okay, on your assignment, which is on page 21 in your packet, which at least this year is blue, I want you to try some problems. There are actually 6 problems on your paper. 2 of them involve right triangles, 2 of them involve squares, one is a circle, and then the other one is a rectangle. So try a few of those problems, pause the video, and then we will look at 2 more examples after you've tried those other problems first. Okay, we've got 2 final examples. So we just need to talk a teeny bit about this first situation. When you drop an object and it's falling to the ground, gravity is causing that item to accelerate. This means that as the object is falling toward the ground, it's falling at a faster and faster velocity. So you can see this boy here dropped this black ball. After 1 second, it hasn't fallen very far, but after 2 seconds, it's fallen this much farther. After 3 seconds, it's at this location. After 4 seconds, it's way down here. And you can see that, it's not falling at the same rate. It's speeding up. If you take physics, or maybe when you take physics, you'll learn how this works a little bit more. And you'll learn a little bit more complicated equations than we're going to use today. But in this class, we're going to give you an equation that will model the situation because our focus is on the method of solving. But gravity does cause an acceleration, which is the reason why these equations look the way they do. Okay, so let's do an example about dropping some sunglasses. So the relationship between the initial height of an object and the time it takes to hit the ground is modeled by the equation h equals 4.9 t squared. This is sometimes also written in function notation. So also, and I think on your paper, it says h of t is equal to 4.9 t squared. This t over here on this side of the equation, that's just the same as when we have f of x. It's just a location for the input. Okay, Christy drops her sunglasses from a bridge that is 100 meters above the river. How long will it take her sunglasses until they hit the river? So we're trying to solve for a time, and we know that initial height of the sunglasses is 100 meters. So the 100-meter height, it goes into the equation in the position of the h, because that is the height above the water. We don't know how long it takes the sunglasses to hit the water, then that t is what we're trying to solve for. And we use t here because it stands for time. So if I want to solve for this t squared, I'm not ready to apply the square root yet because I want to get this t squared by itself before I apply the square root. So we're going to start by dividing both sides of our equation by 4.9. That's going to cancel this one out. 100 divided by 4.9 is 20.408. And now that t squared is isolated, we're ready to apply the square root to both sides. Again, we're not using a plus or minus symbol today because we're not looking for a negative time here. We're looking for a positive time. How long are her sunglasses falling? So if we take the square root, this leads us to the answer t is equal to 4.52 seconds. Our follow-up question is, what if she had been at the top of Angel's Landing? The top of Angel's Landing has a height of 454 meters above the canyon floor. How long would the sunglasses be falling? So this is much higher. Instead of 100 meters above the ground, we're 454 meters above the ground this time. So our equation setup, though, it's going to work the same. Our height is 454 meters, and that's equal to 4.9 t squared. The 4.9 in this equation is related to the Earth's gravitational constant. And again, if you take physics, you'll learn all about that. So again, we want to get that t squared isolated, so we're going to divide both sides of our equation by 4.9. This gives us 92.653. And finally, we need to just take the square root of both sides of our equation, and that gives us 9.63 seconds. So something that is interesting to notice, we talked about that the longer an object is falling, the faster it's going. And you can see that, that has to be true here because we were more than 4 times higher in the second example, but it didn't take 4 times longer to fall. In fact, it only took about twice as long, a little bit over twice as long, but we were over 4 times higher. So at 4 times the height. So anyway, kind of interesting. Okay, last example involves skid marks. Police use skid mark lengths on pavement to help determine the speed of the car if a car gets into an accident. Depending on the road surface, there's different relationships for the length of the skid mark and the speed. But for a dry asphalt road, the length of the skid mark, which is L in our equation, is related to the speed of the car, which is S in our equation. By the equation, L is equal to 1/24 of the speed squared. The length of the skid marks is measured in feet here, and the speed is calculated in miles per hour. So the 1/24 is kind of a unit conversion factor if you've taken chemistry or physics. You might know what that is. Okay, so our equation is L is equal to 1/24 S squared. So after a particular car accident, the skid marks for one car measured 190 feet long. That's the length of the skid mark, so that's going to be the L in the equation. To the nearest tenth, what was the speed of the car? So we're going to solve for S. So we want to figure out the speed of the car when those brakes were applied. So the 190 is going to go into the equation in place of the L, and we are going to solve for speed. So right now we have, with our S squared, we have a 1/24 fraction. 1/24 fraction is the same as dividing by 24. So we're going to multiply both sides of our equation by 24. That's going to cancel the 24 out on the left side. Oh, sorry, that's the right side. I'm not so good with my right and left. Okay, so on the right side of the equation, we have 24 multiplied by 190. That is 4,560. And on the right side, we just have 1s squared now. So we're ready to apply our square root because we have our squared term by itself. We don't need a plus or minus here because the car is not going negative miles per hour. So when we take the square root of 4,560, we get 67.53 miles per hour. And that is the speed of the car. Okay, that was our last example. So there are a couple of practice problems on the back of your blue page. So make sure you try those out. And there is also, for my class, a pair assessment assignment that has 4 questions. So make sure you try to do that assignment before next class. And if you have any questions or anything, we can talk about them next class. All right, thanks a lot.